My friends that are watching on YouTube, are we on? I had forgotten to record this. Sorry about that. I did want to at least mention that we're talking about precipitation, and there are solubility rules on page 156 in the book. You're going to want to look at that. Especially remember the first 3 rules on it. That tells you when or what kinds of ions are always soluble with everything. That's good to know. I will make sure, well, the notes are already on Edline. You're going to want to look at the parts about the precipitation reactions. That's the ones that we're looking at right now. So we went to this slide where we have a couple of solutions that get mixed together, and we're trying to figure out what will precipitate in this mixture of ions. So we did the first one already. We're just looking at the second one here. Aqueous lithium chloride is mixed with aqueous mercury 1 nitrate. I told you I hated the mercury 1, but then I used it anyway in an example. This is the first and last time that I'll deal with mercury 1. What is our precipitate in this one? Now, what ions do we have? We have lithium ions. We have chloride ions. We have this good friend of mine. And then we have nitrate too. I'll just put that over here. When you see nitrate, you should be so happy because you know that's not going to precipitate with anything. So that one's off the hook. The only negative that can possibly make it precipitate is this thing right here. Are you with me? So, is that going to precipitate the lithium? No. Why? Lithium doesn't precipitate anything. No, that's rule number 2 for the solubility rules, is that the group 1 metals are not going to make anything insoluble. So the only choice that we have is for a chloride ion and the mercury 1 ion to precipitate.
Oh wait, like something of the same like original ion can never precipitate anyways, right? Like lithium chloride,
they would not get back together.
Yeah.
No. The truth wants them to, but they won't.
Yeah. Because like they would never split apart in the first place.
That's right. They wouldn't go if they weren't soluble. They're not going to change their mind later on. So they have already broken apart. Sorry. Okay. So is it reasonable to think that chloride and the mercury 1 ion will join together and make it precipitate? Yeah, if I could take you back here, I'll remind you that the chlorides and all the halides, except for fluoride, are soluble almost all the time, except for when there was silver, lead, and there it is right there. It's not soluble. So that's our precipitate in this reaction. And so it's going to mean that we have the, not H2, sorry, Hg2 with a positive 2 plus the chloride ion. What's the formula for mercury 1 chloride? It's so dumb looking. Did you get it? It's Hg2Cl2. And you can't reduce it. Because Hg2 is a polyatomic ion. Remember, we never mess with the formulas of polyatomic ions, even if it looks ridiculous. Now it's not balanced. I'll have to put it 2 right there. That'll take care of it. Yes?
So if it was mercury, aqueous mercury 2, with mercury 2 nitrate, then could we say HgCl2?
Oh, if it was mercury 2, it would be HgCl2. Yeah. But mercury 1 chloride is Hg2Cl2. Anything else about this one? Okay, now the next problem, we only have one more slide that we're going to take on. This is going to be a treat for you. So we're going to get into some stoichiometry. In fact, I'm going to maximize this. And let's take a look at what we have. We're going to mix 2 solutions together and see if we can calculate something now in the reaction. A 100 ml aliquot, I love that word. Aliquot. Have you ever used that word before?
No.
Isn't that good? It's a measured sample is what an aliquot is. So 100 ml aliquot of 0.2 molar sodium hydroxide is mixed with 100 ml of 0.2 molar iron 2 chloride. Write the balanced equation for any reaction that occurs. Do you think a reaction is going to occur between these two solutions? You got sodium hydroxide and iron 2 chloride. I think a reaction will occur because if a reaction didn't occur, then they wouldn't have a letter A here because there wouldn't be any more to ask. So they're going to ask questions later on because there is a reaction that occurs. I'm just going to leave a little bit of room here. Can you find a precipitate? What ions do we have here? We have sodium ions.
Is it asking for the net ionic?
It just says write the balanced equation. So if it says that, you can write it however you want. I'm going to go ahead and write it as the full molecular because I think we're more comfortable with that right now, and I'd rather not throw too much different things at you. We have hydroxide ions. We have iron 2. I'll just put them all over here. And we have chloride ions. There's also sodium. Is there a combination of these two that you would expect to be insoluble? I'm thinking sodium is not going to mix with anything and be insoluble, is it?
No.
The truth?
Wouldn't it be CO2? Would there be 2 CO in the balance equation?
Well, when you write iron 2 chloride, yeah, it's FeCl2. But as soon as that dissolves, are the 2 chlorides still connected to each other? No, they break off and they go off on their own way. So we've got chloride ions. Doesn't matter how many for right now. We just want to know what the precipitate is going to be. You need your solubility rules. Do you have the ions written down? Hydroxide, sodium, iron, chloride. If you find it, tell me. John Hay. Are you stretching your hand out?
Yeah.
Oh, okay. Somebody's got to have it. Wesley, thank you. Sorry? Number 5, yeah. Hydroxides tend to be insoluble with almost everything, except for, of course, the group 1 things. Rules number 1 and 2, they trump everything. Hydroxide is insoluble with almost everything, except the things that are always soluble. And the same thing is true down here, like sodium sulfide, potassium sulfide, that's always soluble. Potassium sodium carbonate, that's soluble like that. So yeah, that hydroxide, what could the hydroxide combine with that's going to be insoluble? The iron, right? The iron. So, when these two when these two solutions are mixed together, you're going to have sodium hydroxide, NaOH, plus the iron 2 chloride, FeCl2, yields. We're going to expect to get Fe, OH taken twice, and NaCl. Just writing a double replacement reaction. And by the way, you are advanced chemistry students. When you take the Fe and the Na and switch places, please do not let me see you write NaCl2. I can handle it in Chem 1. It's a common mistake. It's not a common mistake for you. You can't do that. You know that the charge on sodium is positive 1. The charge on chloride is negative 1. So there's 2 chlorides there. Why? To balance the charges with the iron that it's with. But when it leaves the iron, when that chloride ion leaves the iron, then you don't have that 2 Cl's there. So balance the charges correctly when you write the formulas for the products. Okay? Make sure when you write formulas for compounds, you're balancing the charges. Now, is this equation balanced? It's not. We do need to balance it. Let's see. I think we have to put a 2 there and a 2 there. Do I need the parentheses around the OH when I write this formula?
Yes.
Yes. This is different from writing FeOH2. Okay. Anybody have any questions about that? Our precipitate is this thing right there. I'll just put a star. That's our precipitate. The sodium ions, the chloride ions, they're spectators. They're really not involved. You could write the net ionic equation here. I'm just going to leave it like this. And let's take a look. This title says Stoichiometry of Precipitation. Here it comes. What mass of the precipitate is made? How do we find that? You give them some information about how much of each of these you have, right? Now, last chapter, in the stoichiometry chapter, we started almost all the time with grams of these, and we converted that to moles. Now, and you're going to see tons of problems like this, you'll not start with grams, but rather you'll start with molarities and volumes. Can you find moles from molarity and volume? Yes. You can. Yeah, you're going to do that a lot. I'm just going to write the information that we have. For the sodium hydroxide, we have 100 ml and 0.2 molarity. For the iron chloride here at the end, we have 100 ml and 0.2 molarity of that. The question is, what mass of precipitate is going to form? So there's our precipitate. We want to know how much of that iron hydroxide are we going to get. What do we have to do to be able to find how much product we get, Wesley? Yes, that's what I'm hoping to hear. We know the amount of both reactants. We need to find the limiting reagent. That dictates how much product we get, right? So this is rich in stoichiometry. Can you convert both of these to moles? You know how to multiply. I just answered my own question. You know how to find moles from molarity and volume, right? You multiply them. By the way, this milliliters here for the volume, is it necessary to convert that to liters, or can we just leave it in milliliters? Do we need liters? What's the definition of molarity? Moles per liter. I think we have to have the volume in liters. So, I mean, you can leave it like that. You don't have to like cross it off or erase it and put liters. But when you multiply volume times molarity, remember this thing, M, that's molarity equals moles over liters. Finding moles, that's what we're trying to find. You have to multiply the molarity times the liters. Molarity times 0.1. So the number of moles of this reactant is 0.02 moles. I just lost all my sig figs, and I did that for a reason. I'll tell you in a second. This times this, 0.1 times 0.2 is 0.02 moles as well. Which one runs out first? You're starting with the same number of moles of both of these. Which one is going to be the limiting? Or do they both run out at the same time? You're voting for NaOH? Why, Mina? Yes. You use twice as much NaOH as iron chloride, don't you? They react in a 2-to-1 ratio. For every one of these that reacts, 2 of these reacts. So if I reacted 0.02 moles of this, how many moles of this would I need? I need 0.04 moles of that to use all that up. I don't have 0.04, I only have 0.02. See that? Or you can look at it and say, do I have twice the number of moles of NaOH as iron chloride? No, I don't. This is my limiting reagent. Okay, fine. So we're going to go from moles of our limiting into grams of iron hydroxide. The reason that I just lost all my sig figs here is because I want to encourage you, try to do these without a calculator. Let's see if we can just estimate the answer. No calculators allowed today. I want to try to help work with you to get you to be more comfortable with this whole no calculator business. All right? So let's see if we can do this. Remember, this is our limiting, so all that's going to get used up. 0.02 moles of NaOH times, going from that to that, it looks like a 1-to-2 ratio. 1 mole of iron 2 hydroxide over 2 moles of NaOH. I want grams, not moles, though, so we've got one more step. And, okay, well, we couldn't use our calculator. What are we going to do here? Iron has what molar mass? Do you know iron? Anybody? It's 55.8 on the periodic table. Juliana, do you want to go with 56, though? If we're estimating, my gosh, don't use any decimal numbers when you estimate. Be easy on yourself, and just let's call it 56. So it's 56 plus 2 hydroxides. 16 plus 1 is 17 times 2 is